Hi there. In this video, we're going to continue looking at expansion work, and we're looking at a very specific kind of expansion called Pascal's triangle expansions. And they deal with expansions like we saw perfect squares before, right? Where we had two things and a binomial expression that was raised to the power of two. Well, we're going to do what we can to raise bigger and bigger powers like power of three, power of four, power of five, and so on. But let's start by talking about Pascal's triangle because it's kind of important to the methodology behind these bigger expansions. And if you've done 9 maths extended at friends, you'll have come across Pascal's triangle, whether you remember or not, I don't know, but here it is in a nutshell. What we do is we start off with the top of our triangle being a 1, like so, and then we put two ones as the next row in the triangle, and then each subsequent row is built like this. We start with a 1, and then we add the two numbers directly above to create a new number, 2. And then we always finish with a 1. Let's do it again. 1, and then add the two numbers above together to get a 3. Do the same thing for the next pair, and we get a 3. And then we finish off with a 1. I won't put the arrows in anymore, but maybe I'll just verbalize it. We've got a 1 to start with. Above is a 1 and a 3, so that makes a 4. Above the next is 3 and a 3, which makes a 6. And above the next is 3 and 1, which is a 4. And then we finish with a 1. And then we do the next row. Maybe you'd like to pause the video and do the next row yourself. You either paused it or you didn't. I'll quickly go through it. 1, and then 5, and then 10, and then 10 again, and then 5, and then 1. So if that doesn't make sense, make sure you let me know so that I can sort of help you out there. But it forms this kind of triangular shape here that's made up of all these numbers with these patterns. There's a few patterns that we can see, like there's 1s along here, there are 1s along here, it goes 1, 2, 3, 4, 5 here, and so on. An important pattern to see is that if I drew an imaginary line down the middle here, we would have a beautiful symmetrical pattern. So if I go to say this row here, on the left of this middle, I've got half a 6, if you like, 4, 1, and then on the other side, I've got the 6, 4, 1 as well. If I go down to the next row, there's 10, 5, 1, and 10, 5, 1 here. So it's all symmetrical, sort of builds up and then goes down again in a symmetrical way. Okay, so in a moment, I'm going to explain why this is important for these expansions. Let's have a look at the first example I've got there. You can see I've said pause video and expand. Let me explain first what I want you to do, and then you can pause the video. We've got x plus 1 cubed. Now, what we're going to do is we're going to break that cube down to two component parts. Now, I'll show you with numbers first, which I'll then erase, and then we're going to do the same thing with this. So I've got 2 cubes, say, for example. I could, if I wanted to, break that down into 2 multiplied by 2 squared. Sometimes I write this like this, by the way. Instead of having a multiplication sign, I just put the next bit in brackets so that the multiplication is implied, not written, but it's there. So 2 times 2 squared. Now, left-hand side is still equal to the right-hand side, right? 2 cubed is 8. 2 times 4 is equal to 8. So all I've done is I've split it into 2 different factors. I'm going to use the same logic here, but with a more complex expression, but it's still a number. X plus 1 is still a number. Don't know what x plus 1 is, but it's a number, so number rules apply. So I'm going to go x plus 1 is equal to x plus 1 all cubed, is equal to x plus 1 multiplied by x plus 1 all squared. So I've just broken it down into 2 factors like that. Now, the next thing I'm going to do is I'm going to leave x plus 1 here by itself, but now I'm going to use my understanding of perfect squares in order to quickly expand that. And again, if you're not quite there yet with your perfect square patterns, keep practicing them because it makes your life easier. X plus 1 squared. So we know that for a perfect square, we square the first term. We then square. We squish these two terms together, multiply them together, and double it. So x times 1 is x. Double it to get 2x. And then I've got 1 squared, which is 1. So I've now expanded it. Now you can use the chicken beak method or you can use your box method in order to complete this expansion. Pause the video and finish the expansion. Okay, if you have done that correctly, you would have something like this. I'll do it slowly so that we can sort of see it in this example. 1 times x squared, sorry, x times x squared is equal to x cubed. Again, you could use the box method. I'm just using the chicken beak method myself. You don't have to draw these lines in if you don't need them. I find it a useful visual aid. X times 2x is 2x squared. And then finally, x times 1 is equal to x. Now do the bottom of the chicken beak. 1 times x squared is equal to x squared. Notice how I'm using my column addition here to keep it all nice and neat. 1 times 2x is equal to 2x. And finally, 1 times 1 is equal to 1. And now I'll just finish that off by collecting like terms. X cubed, I've got 2x squared plus x squared, that's equal to 3x squared. I've got x plus 2x, that's 3x. And I've got my plus 1, and now it's expanded. It takes a while, but we can do it. Similarly, for x plus 1 to the power of 4, I'm going to start you off, and then you can pause the video and try and finish the expansion yourself. I'm starting you off because I don't want you to make the mistake of maybe going, well, that's x plus 1 all squared times x plus 1 all squared. You could do it that way, but a slightly smarter way would be to go x plus 1 multiplied by x plus 1 to the power of 3. Okay, so that will multiply together to give me x plus 1 to the power of 4. But now I can use the result that I've just found here, to replace with this expression here, and it makes my expansion a little bit better. So my next line would be x plus 1 multiplied by x cubed plus 3x squared plus 3x plus 1. And now I can expand that. I'll give you a moment to pause the video and come back once you're done. Okay, let's see if you got the same answer as me. I'm not going to do all the slow working out. I'm just going to go straight to the answer here. So you should have got x to the power of 4 plus 4x to the power of 3 plus 6x to the power of 2 plus 4x plus 1. If you didn't get that, you got lost in the way, make sure that you ask me questions in class so that I can help you out as we go along. Okay, let's have a look at this last one, x plus 1 to the power of 5. I'm not going to make you do this longhand because I suspect it would drive you silly, although you could use a similar process before. We've just worked out what x plus 1 to the power of 4 is, so you could use that in order to work out x plus 1 to the power of 5. But I'm going to go straight to the answer. I promise you I haven't prepared this beforehand. I'm just going to do it straight from my head. Not because I'm smart, but because I know the shortcut, and that's what you're going to learn next. So here we go. Without any prior thinking, I can just go, that's x to the power of 5 plus 5x to the power of 4 plus 10x to the power of 3 plus 10x to the power of 2 plus 5x plus 1. And I'm done. Okay, so you too can learn the magical mystery arts of expansion in a very, very quick way, so that you don't have to do all of these lines of working out in order to just get to that result there. Okay, before I go any further then, before I unpack it all, I want you to have a look at the end results for each of these lines here and see if you can pick any patterns out. Pause the video, have a look at it. There's two patterns I want to point out. The first one is that if you look at the powers of x, they are going down by 1 each time. 3, 2, 1. And then it's not written here, but we could put an x to the power of 0 here, because x to the power of 0 is just 1. Anything to the power of 0 is 1. So we've effectively got x to the power of 3, 2, 1, 0. Oh, again, the 1's implied. It's not written there, but it's implied to be 1. 3, 2, 1, 0. Here we've got 4, 3, 2, 1, 0. And here we've got 5, 4, 3, 2, 1, 0. So that's the first pattern. It goes down in descending powers of x, with the highest power being the same as the power of the expansion. The other thing I want you to see is that just like in Pascal's triangle where we have symmetry, we also have symmetry here as well. An implied 1. The number 1 could be written here because anything multiplied by 1 is itself. So 1, 3, 3, 1. 1, 4, 6, 4, 1. It's symmetrical. 1, 5, 10, 10, 5, 1. Each time it's symmetrical. But there's another factor that we need to think of as well. See if you can have a look at these expressions here and how it might relate to Pascal's triangle. Pause the video if you need to. You may have seen that the numbers that form part of these terms, the one here that's implied 3, 3, 1, the one that's implied here 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, are actually numbers on these rows here. I don't want to keep on calling them numbers because it's not the right phrase to use, and we're going to use it a lot. So let's get it right. The number part of the term is called the coefficient. So if I had root 3 multiplied by x, root 3 would be the coefficient. 2x, 2 would be the coefficient. Half x, half would be the coefficient. It's the number part of the term. And the coefficients of the expansion equate to the coefficients in a particular row of Pascal's triangle. So that's a really important point to make there. That's how I was able to quickly go to the answer, because all I did is I looked at my Pascal's triangle here and went 1 times x to the power of 5, and then I kept on going down by 1 power of x. 5 times x to the power of 4, 10 times x to the power of 3, 10 times x to the power of 2, 5 times x to the power of 1, 1 times x to the power of 0. Didn't bother writing an x to the power of 0 for obvious reasons. And that's how I did it so quickly. How do you know which row to pick? Well, you can count them as long as you start with 0. 0, 1, 2, 3, 4, 5. So for x plus 1 to the power of 5, it's the 5th row. Or if you look at this diagonal here, it's the row that has the 5 in it along the diagonal. So this is the expansion for it. And I call these numbers here the starting coefficients for the expansion. They're not always the ending coefficients, but they are the starting coefficients. And that'll make sense when I look at some examples in a further video. It does work for all powers. So like x plus 1 to the power of 0, for example, is just 1, and there's the 1 there. X plus 1 to the power of 1 was just x plus 1. So 1 and then 1. X plus 1 to the power of 2 is just our square. 1, 2, 1. 1, 2, 1. So it perfectly works for all expansions from x plus 1 to the power of 0 to x plus 1 to the power of 5. Okay, let's have a look at it in practice a little bit more. We won't worry about these two. I was going to get you to write it out a bit more, but we're not going to do that. Sorry, just a pause because someone came into the room. I won't do this bit here, and we'll move on to these examples here, where instead of having a 1 at the end, I've got a y. Now, I'm going to just explain to you how it all works, but if you did the expansions manually, you'd see that it definitely works what I'm about to show you, but I'm just going to go straight to the pattern. So I'm going to start off the way I did before, and that is I'm taking the row that corresponds to a power of 3, which is 1, 3, 3, 1, and now I'm going to do the expansion straight up. And I'll come back to the y bit in a second. So I got the 1, which I'm not going to write in, x to the power of 3. And then the next number is 3. So I'm going to go plus 3. And then I'm going to take the power of x down by 1, x squared. And then I'm going to write the next starting coefficient, which is 3. And then I'm going to take the power of x down by 1 again. So it's now just x to the power of 1, but we don't write the 1 in. And then I'm going to write down the 1 and x to the power of 0, which we're not going to write in either. So that's our starting coefficients. But now I'm going to draw in a different colour what happens to the y. Well, as x goes down in power, y is going to go up in power. So this is the second term. So here we're going to start with the lowest power, which is y to the power of 0. So we don't write it in. The next one is y to the power of 1. So that's just y. The next one is y to the power of 2. So that's y squared. And the last one is y to the power of 3. And I'll just write it without colours and getting rid of coefficients I don't need. So the expansion is x cubed plus 3x squared y plus 3xy squared plus y cubed, and you're done. Okay, so you can see invisibly sometimes, but they're there. 1, 3, 3, 1, 1, 3, 3, 1 as the coefficients. And we've now got descending powers of x, 3, 2, 1, 0 for powers of x, and ascending powers of y, 0, 1, 2, 3. And as long as you follow that pattern, you can basically do any old expansion that you need to do of this form, something plus something to the power of a number. Oakley dokley. what happens if we've got a subtraction like we have in slide 8 here. So if you've got a subtraction, you don't have to do this for real, but you you don't have to practically do this, but in your head, remember that a subtraction is really just the addition of a negative. So for example, 10 minus 4 is 6, which is the same as 10 plus negative 4, which is 6. So why is that useful? I'll show you in a second. Remembering that you're simply adding a negative, you can do the same thing again. We go which equals, and I'm going to start off with the first coefficient, starting coefficient, which is 1. So 1, x to the power of 3, and then not y, but minus y to the power of 0. Doesn't matter there's a negative. To the power of 0 simply means that's equal to 1, so we don't write it in. And then we've got 3, and then I'm going to use my bracket notation again instead of multiplication. 3 multiplied by x to the power of 2 multiplied by minus y to the power of 1, and we're not going to write the 1 in, plus 3x, go down 1 power, I've got the 1 in, but I didn't need to write it in, minus y squared, plus 1 multiplied by x to the power of 0, we're not going to write it in, multiplied by negative y to the power of 3. So as long as we keep our negative with our term as we go along, it'll all work out, and I'll explain why in a second. Simplifying, x cubed plus, well, I've got 3 multiplied by x squared multiplied by negative y. So we're going to end up with a negative term here. So instead of having plus, I'm going to have minus. So I'm going to have minus 3x squared y. Okay, we're multiplying a positive by a negative. In the next term, I've got 3 multiplied by x, and then I've got negative y squared. But if I square a negative number, I get a positive number, right? So that means I'm ending up with plus 3xy squared. And then finally, I've got minus y cubed. Well, if I raise a negative number to 3, say, let's just say, I'll erase this in a second, but if I had, say, negative 2 cubed, well, that's negative 2 times negative 2, that gives me positive 4, times negative 2, which is equal to negative 8. So when I raise it, when I raise a negative number to 3, I'm going to get a negative result again. In general, and this is the important point to take out, is that if you raise a negative number to an even power, power of 2, power of 4, power of 6, power of 8, you're going to get a positive result. But if you raise a negative number to an odd power, power 1, power 3, power 5, power 7, you're going to get a negative result. So negative y to the power of 3 is going to be negative y cubed. Notice the pause there, negative y cubed. But if you raise it to an even power, like negative y to the power of 4, then you're going to get a positive number. You're just going to get y to the power of 4. Okay, so what does that mean? So to finish off this problem then, I've got a negative y cubed at the end, so I'm going to get negative, I'll just do that in the right colour, negative y cubed. Okay, one last point then. Some people like this idea of bringing the negatives through. It's less confusing for them because it's the same pattern, but we're just keeping track of our negatives and whether they're positive powers, odd powers or odd powers or even powers. But the other thing to note then is that when you've got a subtraction that you're trying to expand here, really the pattern will always be positive, negative, and so on. So if I had x minus y to the power of 10, it'd just be positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, all the way. Okay, hope that makes sense. In the next video, I'm going to go through some example problems, but that's it for the theory. Let me know if you've got any concerns over the concepts.